Hello everyone, today we have a report about curve fitting. In this report we have a problem solved by curve fitting. We use in this problem linear regression and the regression of degree 2 to solve this problem. This report created by Ali Anwan and Ahmed Akram. Introduction. Given a set of data, we might want to approximate the value in between, after or before what is given. To do this, we can generate a curve by using either interpolation or curve fitting. Interpolation is a method of estimating the value of a function at a given point within the range of a set of known data points. It involves finding a polynomial that fits a set of data points exactly, rather than just approximating them. Curve fitting, on the other hand, is the process of finding the best fitting curve, where the goal is to find a model that captures the underlying trends in the data, rather than fitting the data point exactly. For example, suppose we are given the following data points. Perhaps this data represents the temperature over several days, or the location of a board over the past several hours. We are wanting to estimate what the temperature was, or where the boat was, in between data point D and E. To do this, we first use interpolation that generates a polynomial that exactly matches the data set. In general, if we are using interpolation on a point, we can use a polynomial of degree n-1. In this case, we will use a polynomial of degree 4. Dynamical analysis of a linear actuator system for precision control. The problem. In the context of a mechanical system employing a linear actuator for precise linear motion, there is a need to conduct a comprehensive dynamic analysis to understand the system's behavior, response, and energy efficiency. Under varying operational conditions, a dataset representing the relation between the actuator position x and the corresponding output force y is available. X equal 1, 2, 3, 4, 5, 6, and y equal 6, 4, 3, 5, 4, 2. Now we have objective. Perform a detailed dynamic analysis of the linear actuator system, considering its interaction with external loads and environmental factors to optimize its performance and energy utilization. Key consideration: 1. The actuator system should operate within a specified range of position and external loads. 2. Evaluate the system's response time, accuracy, and energy consumption under different loading scenarios. Proposed steps: 1. A mathematical model based on the given dataset to represent the actuator system's static behavior. Least squares straight line equation y equal ax plus b. 1. Integrate the static model into dynamic model that considers the system inertia and damping and external loads. 2. Perform simulation to analyze the dynamic response of the actuator system under various load conditions. 3. Identify critical parameters affecting the system dynamic performance and energy efficiency. 4. Optimize the actuator system design and control parameters to achieve enhanced dynamic response and reduced energy consumption. Constraints: 1. The actuator system must meet or exceed specified force requirement. 2. Consideration of real-world constraints such as manufacturing tolerance and material properties. Expected deliverables: 1. Dynamic model equation describing the actuator system behavior. 2. Simulation results illustrating the system's response under different operation conditions. 3. Recommendations for optimizing design and control parameter for improved dynamic performance and energy efficiency. 4. Documentation of the analytical approach, methodology, and finding. Now we solve the problem. We have here data for the problem. X equal 1, 2, 3, 4, 5, and 6, and y equals 6, 4, 3, 5, 4, and 2. Solution: for linear regression, we have this equation: f equal ax plus b. We have partial f over partial a equal x, and partial f over partial b equal 1. Summation from I equals 0 to infinity yi minus axi minus b, that's all across xi, equals 0. This equation number 1. The summation from I equals 0 to infinity yi minus axi minus b equals 0. This equation 2. From equation 1, 1 over n, summation from I equals 0 to infinity yi xi equal a over n, summation from I equals 0 to infinity x square I plus b over n, summation I equals 0 to infinity xi. We have this equation: myi equal a mx square I plus bmxi, this equation 3. From equation 2, we have 1 over n, summation from I equals 0 to infinity yi equal a over n, summation I equals 0 to infinity xi plus b. We have this equation: myi equal a mxi plus b, this equation 4. We have this equation 3 and 4, and we have to find x cross I and x square, only x and only y. We have here x, only x and only y. Only x is 1, 2, 3, 4, 5, and 6, and only y 6, 4, 3, 5, 4, and 2. And when we cross them, we have this number, and we have to find x square. 1 square is 1, 2 square is 4, 3 square is 9, 4 square is 16, 5 square is 25, 6 square is 36, and we have to find the summation for each one. Summation for x is 21, summation of y is 24, summation for xy equal 75, summation for x square is 91. And now we have to find m equals summation over number of data. Number of data is 6. So mx equals 21 over 6 equals 3.5. My is 24 over 6 equal 4. Mxy equals 75 over 6 equal 12.5. Mx square equal 91 over 6 equal 15.16. And now we have to substitute this number in equation 3. We have this equation: 12.5 equal 15.16a plus 3.5b. And we have to put this number again in equation 4. We have this equation: 4 equal 3.5a plus b. We have to put this equation in this equation to get a and b. We get a equal minus 0.515 and b equal 5.804, and we have to put this number in original fraction. We have f equal minus 0.515x plus 5.804. Now we have to substitute x in this equation to find f. Then we have to find y minus f for each one and find summation for this number and square it. We have 0.81 cross 10 to power minus 4. Now we have to solve the problem in regression of degree 2. We have this function f equal ax square plus bx plus c. We have partial f over partial a equal x squared, and partial f over partial b equal x, and partial f over partial c equal 1. And we have summation from I equals 0 to infinity yi minus ax square I minus bxi minus c. That's all cross x square I equals 0. This equation number 1. And summation from I equals 0 to infinity yi minus ax square I minus bxi minus c. That's all cross xi equals 0. This equation 2. And summation from I equals 0 to infinity yi minus ax square I minus bxi minus c equals 0. This equation 3. From equation 1, we have 1 over n summation from I equals 0 to infinity yi x square I equal a over n summation from I equals 0 to infinity x to power 4I plus b over n summation from I equals 0 to infinity xi to power 3 plus c over n summation from I equals 0 to infinity xi square. And we have myx square I equal an xi to power 4 plus bmxi to power 3 plus cmxi square. This equation 4. From equation 2 we have 1 over n summation from I equals 0 to infinity xi equal a over n summation from I equals 0 to infinity x square I plus b a over n summation from I equals 0 to infinity x square I plus c over n summation from I equals 0 to infinity xi. And we have mxiyi equal amxi to power 3 plus bmxi square plus cmxi. This equation number 5. From equation 3, 1 over n summation from I equals 0 to infinity yi equal a over n summation from I equals 0 to infinity x square I plus b over n summation from I equals 0 to infinity xi plus c. My equal a mxi plus mxi plus c. This equation number 6. Now we have this equation 4, 5 and 6, and we have to find x square cross y, x to power 4, x to power 3, x square, and x cross y, and only x, only y. We find it and wrote in this table, and we have to find summation for each one. Then we have to find m for each one by deviation summation over number of data. Now substitute into equation 4. We have this equation 15.2 equal 379.2a plus 73.5b plus 15.16c, and substitute into equation 5. We have equation 12.5 equals 73.5a plus 15.6b plus 3.56. Now substitute into equation 6. We have 4 equal 15.16a plus 3.5b plus c. After we substitute equation, we find a equal minus 1.47, b equal 8.53, c equal minus 3.54. And when we put this number in original fraction, we have f equal minus 1.47 x square plus 8.53 x minus 3.54. We have to substitute x in this equation to find f. Then we have to find y minus f for each one. Then find summation for this number. We got minus 0.12. Then we have to square it. We got 0.0144. So using the linear regression function is better and more accurate than the regression of degree 2 because the deviation square is smaller than the deviation square of the regression of degree 2. So the approximate function for this data is y equal minus 0.515x plus 5.804. Thank you.